The first approach in looking for the function of a given dataset is through method of group averages. This video shows the solution of an even-numbered sample. Welcome to Numerical Solutions to C Problems. The approximate approach of curve fitting needs to minimize the errors, if not zero it out. And with this method, the concept is to have the positive errors balance out with the negative errors so they can cancel out. The definite algorithm of group averages starts by dividing the dataset into two tables. In case there is an excess pair of coordinates, the first table would absorb it. Next is to take the summation of the x and y values in order to solve the average of each variable. Having an average x and y values, place them into the slope-intercept format of a linear function. Then through simultaneous equations, solve for a and b. Then again, these variables are placed into the required function. Let's take the sample dataset in looking for the function of the best fit line. Observe that the dataset contains 10 data points, which can be divided exactly into two groups. The first table contains x values from 0 to 4, including their y counterparts. The second table includes x of 5 until 9, with their y pairs. This is step 1. The next move is to take the summation of variables. 0, 1, 2, 3, and 4 add up to 10. And the y values also turn out as 12.19. From the second table, 5, 6, 7, 8, and 9 become 35. And their y counterparts add into 52.265. With the summation already identified, we can take the average, where with each column, the total is divided by 5. Thus 10 upon 5 is 2. 12.19 divided by 5 is 2.438. From table 2, 35 over 5 is 7. And 52.265 divided by 5 is 10.453. These averages are what we need to come up with the partial functions. Place x and y averages into the function y as equal to ax plus b. So from the first table, we get 2.438 as equal to 2a plus b. From the succeeding table, we get 10.453 as equal to 7a plus b. Remember that our goal is to determine the variables a and b. And having two equations, we work on simultaneous equations to be able to find the variables. This can be done using your scientific calculators, but we can also work on it manually through elimination. So by subtracting the two equations, we come up with negative 8.015, and this is equal to negative 5a. Variable b cancels out from the two functions. Divide the function by negative 5 to have a as 1.603. With a already figured out, plug it into any of the functions generated. In this case, we use the first table. This becomes 2.438 as equal to twice of 1.603 plus b, giving b as 0.76. With a and b already known, we finally have the function for the best fit line of the dataset as y as equal to 1.603x plus 0.76. Using the same dataset, what if what we needed to look for is the best fit quadratic curve? For this function, always make clear which point shall the curve pass through. In this example, the point where the curve is preferred to pass is at 4, 505. Since this is the initial video for this method, we will be deriving the functions used in the process, although you can readily fill out the other columns by using patterns. From the quadratic equation y as equal to ax squared plus b of x plus c, taken as the first equation, we create another by using the intersected point, making the second equation 5.05 as equal to a times x squared of 4 plus b times 4 plus c. Next is to subtract these two functions. This makes y minus 5.05. Then for the next term, we have ax squared minus a times 4x squared. If we factor out a, we get a with a binomial of x squared minus 4 squared. Do the same with the next term. bx minus b times 4 becomes b times the binomial x less 4 when we factor out b. And again, c cancels out. Next is to note that x squared minus 4 squared has the form of difference of two squares. And we are gonna expand this to simplify the whole function further. The first term stays the same, then we get a times the sum on the difference of two terms, which are x plus 4 and x minus 4. Then also b times x minus 4. By the expansion, notice that there is a redundant binomial x less 4, which we are to factor out again. So the function becomes y minus 5.05 as equal to the factored binomial of x minus 4 multiplied by a with x plus 4 plus b. Take out x minus 4 from the right, making y minus 5.05 all over x minus 4 as equal to the binomial of a with x plus 4 plus b. Now if we compare this resulting function into the format we are dependent on, y is equal to ax plus b, we take the ratio of y minus 5.05 with x minus 4 as y, and also x plus 4 as x. But then be extra careful that although we are using the same variables, we have the transformed function with capital Y and capital X instead of the original function using small x and y. So how do we look for the function of the quadratic curve for the dataset? We still divide the whole thing into two, but then we add two more columns for positive x, which we have derived earlier as x plus 4. Then capital Y, also derived earlier as y minus 5.05 all over x minus 4. Fill out the table again, starting with capital X, where we have 0 plus 4 as 4. And the rest of the column is filled out using small x plus 4. The other column then starts with 0.015 minus 5.05 all over 0 minus 4, giving 1.2588. Do the same with the other values, but then take note of the last value. This is solved as 5.05 minus 5.05 all over 4 minus 4. Because of a zero denominator, any device will show undefined answer, but we are to simplify it as just 0. With the columns completed, take total x as 30 and total y as 5.2971, which again will be taken the average. That is 30 divided by 5 as 6 and 5.2971 divided by 5 as 1.0594. So the first equation is then taken as 1.0594 as equal to 6a plus b using the format of y is equal to ax plus b. We repeat the process for the second table. Fill out the column for capital X as equal to x plus 4. The next column is also for capital Y, which is computed as y minus 5.05 over x minus 4. After which, take their total. 9, 10, 11, 12, and 13 add to 55. Then capital Y is also added to 9.4519. Again, take their average. That is 55 divided by 5 as 11, and 9.4519 divided by 5 as 1.8904. So the second function from the table is 1.8904 as equal to 11a plus b. Take the two functions and solve for the variables a and b. Again, you can use the simultaneous equation function of your scientific calculator. But just the same, we manually solve it for our discussion here. By subtracting these two equations, we arrive at negative 0.831 as equal to negative 5a, where a is then solved as 0.1662. Place this value into any of the equations. Again, we use table 1 for our discussion, making 1.0594 as equal to 6 times 0.1662 plus b, making b as 0.0622. Now that we have solved a and b, the only one we need is c. But with which equation shall we generate the value of c with? From our derivation earlier, we started with the quadratic equation, then substituted the coordinates into the function, thereby having 5.05 as equal to a with 4 squared plus b of 4 plus c. Place the solved values of a and b into the equation, now making 5.05 as equal to 0.1662 times 4 squared plus 0.0622 times 4 plus c, giving out c as 2.142. Having found the three variables, we can therefore write the best fit quadratic curve for this dataset as y, which is equal to 0.1662x squared plus 0.0622x plus 2.142. In case we are to look for the best fit exponential curve, how do we go about it? Although creating two groups will still be the initial step, we have to derive how to get the values of a and b this time. The exponential equation is y is equal to a raised to x multiplied by b. We needed to bring down x from its exponent status, so we use laws of logarithms. With the multiplication rule, we can then expand the right side of the function, thereby making log of y as equal to logarithm of a raised to x plus logarithm of b. Then with the power rule, we can take down x, now having log of y is equal to x with log of a plus logarithm of b. Align this with the format of y is equal to ax plus b, where y is then logarithm of y. Take note that this is capital Y because of the transformation. Then from the right side, there are capital A as logarithm of A and capital B as logarithm of B. Before applying this derivation into our dataset, let's look at the function a little closer. Note that there is another column for capital Y, but then x remains as it is. So there are only three columns in solving best fit exponential curves. The first table then contains x from 0 to 4, with an added column for capital Y. Fill up the third column taking the logarithm of 0.015 as negative 1.8239, log of 102 as 0.0086, and so on until the column is filled. Next is to take the total. Remember that what we needed are x and capital Y. So total x is 10, and the summation of capital Y is negative 0.16. Their averages are 2 for x and negative 0.032 for capital Y. Thus, the function from table 1 is negative 0.032 as equal to 2a plus b. From the second table, fill out the third column, then take the summation of x and capital Y. X comes out as 35 and y as 5.0489, making x average as 7 and capital Y average as 1.0098. The second equation then is 1.0098 as equal to 7a plus b. With the two equations already generated, solve them simultaneously through your calculator, or just subtract them to have negative 1.0418 as equal to negative 5a, where a is then solved as 0.20836. This is capital A. To solve for a, use exponential rules, which is e raised to capital A, or that is e raised to 0.20836, giving a as 1.2317. B is then solved from one of the equations where a is plugged in. Say we take the first function, negative 0.032 as equal to twice of 0.20836 plus b, and b is solved as negative 0.4487. And b as e raised to b is then e raised to negative 0.4487, which makes b as 0.6385. Plug these two values into the exponential function and have y as 1.2317 raised to x times 0.6385.